the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 105, where today we're going to be talking about the history of particle physics. Just the ancient, from when we didn't even know what particles were, to our current understanding of the Standard Model. So, that's our idea.
Yeah, this episode has been requested by a few people.
Quite a few.
And if you're interested in, maybe a little bit more in detail episode of the podcast, we do have an episode with Dr. Pekka Nervo where we talk about particle physics and the Standard Model, and more specifically his involvement in the actual history of the development of the ideas that we know today.
We also have
we
have Dr. Don Lincoln, if you want to add that in there, who literally was part of the discovery of the top quark. So that's just phenomenal. So that's also another episode that you could check out if you're interested.
I don't know if it counts as particle physics, but also with Dr. Miriam Diamond, we spoke about kind of like dark particle physics, maybe some type of ideas behind there. So we've covered the topic a little bit, but today we're gonna go through the entire timeline, more or less, at the end of the day.
More or less. I think
this is just a conversation,
Exactly. It's not going to be a cut to cut this, then that, then this. I mean, we're going to obviously keep it chronological, but it's not every single event that we're going to cover. The big ones, maybe. And then also, obviously, maybe end with, our current understanding or lack of understanding of the dark particle physics side of it. So, before we get into the episode... Okay, you want to...
Yeah, I was just going to say there are a lot of unanswered questions today in physics, which, particle physics is kind of the central, is basin the word, where, all of kind of the outer topics kind of leak into, where if you don't know something about electromagnetism, you can always say, is there kind of something that exists which inherently takes the form of a particle, because, we have radiation and we have baryonic matter, things like that. But we all refer to everything as particles, even though some don't have any mass, they're still particles, right? So if we don't understand something about ENM, we ask, is there maybe a particle that we just don't know exists? If we don't know something about gravity, we say, are there dark particles that we just cannot detect? Things like that. So kind of all of the general surrounding ideas kind of revolve around particle physics, which is why it's something so fundamental. When you're born and you open your eyes, you see things, right? So obviously you're asking, what are those things made of?
I think particle physics is almost as fundamental as it can get,
Yeah.
Because I don't think you can get more fundamental, because that's the whole purpose of particle physics, is the most fundamental thing in the universe, or at least the search for that.
You also build, everything in physics builds on top of particle physics, because as soon as you start talking about quantum mechanics, you're still talking about particles, but more so how particles exist and evolve through time. And if you're talking about classical mechanics, is how bigger collections of particles evolve and interact with each other. And, same thing with electromagnetism and all that stuff.
Yeah. It's basically broken up into particles. So that's the idea of today's episode. And let's get into, before obviously the episode, our classic comment of the episode. And today we have the comment of the week as Zerial. Thank you, Zerial. Zerial says, though we are entirely from different continents, I can still feel your emotions related to math and physics. I'm in grade 11 from India, very much interested in math and physics, and now more motivated to devote my time inside this field. Thank you. Well, thank you for that lovely comment.
Yeah.
It was an absolute hoot to read. Thank you, everyone, for all of your comments every week, just that we say the one. So yeah, that's the comment of the week. Any news that we have to bring to the table?
Not really. You know, everything's still
Everything's
going.
just going.
You know.
Oh, big news, big news. I mean, not big news, but we've been saying this, but we are going to now, hopefully within the next episode or 2 episodes, have the merch store ready. When it will be live, we're still not sure because we still have to make sure the shipments are ready and whatnot. So that might take a little bit, but the merch store should at least be done because we had a little technical glitch with that. So that should be done within the next 2 episodes. So whoever's ready, because I know a lot of people have been, texting us, DMing us and whatnot. When is it coming? So here we are, just letting you know. Patience. It's coming.
Also, yeah, we haven't been doing the NFT giveaways, just because it's like it's a whole deal. But let's say this: next time we go live on Instagram, we will give away an NFT live on Instagram. So
nice.
if you want to go follow us at math.physics.podcast on Instagram and stay tuned for the live, we will be giving away, I think it's number 5 or number 6 that we're giving away now.
I think it's 5. I think it's 5.
Yeah. So stay tuned. Anyways, let's talk about particle physics. One thing that I wanted to say, which is kind of funny enough, is that when you get into field theory, is it called?
Yes.
It's quantum field theory.
Quantum field theory, QFT,
right?
Yeah.
We actually don't even consider particles anymore, right? We just consider like excitations of fields.
Mm-hmm. Those are particles, right? Or at least our
exactly.
Exactly.
And you could think of, or I guess even going into like string theory, which is a little bit more out there. Particles are just these strings that vibrate, quote unquote, at different
That's
frequencies, different patterns. Yeah,
now
exactly.
String theory is just completely different. I mean, it's kind of not that. It requires a lot. I mean, we've spoken about the absurdity of it a lot of times on this podcast, but it requires a lot of extra math that we're just like, sure, it could exist, but we have no idea. The whole 11 dimensions thing. So there are a lot of add-ons. Also, I wanna make sure the excitations in the field are just a specific type of particle. Obviously, it's not all particles. Those are just bosons. We'll get into them, but that's just one specific type. And QFT or field theory in general is mainly just looking at, after Thomas Young and whatnot, all those subsequent experiments, we can now describe them kind of together. At least these bosonic particles like photons and whatnot can be represented as waves or fields, I guess. So we can start to think of them that way. So it's kind of a powerful technique using other methods to still substitute for particles, but still getting the particle out of it.
Right.
I think Parker is frozen.
So I wanted to start with that idea.
Okay.
Because, how did we get there? How did we get to that point where it's such an abstract description for just people, if you were to go up to somebody on the street and be like, what do you think particle physicists are working on / not necessarily particle physicists, but what do you think physicists are doing nowadays and how they're describing matter? It's just so out there. But how did we start? Well, we started by opening our eyes, or I guess we actually started by becoming conscious.
Right. I guess
asking questions.
To that. Yeah.
Right.
Yep.
I feel like we start a lot of episodes like that. It all started when we were born and we looked around. Okay, so what do you see, right? As a caveman, what do you see? You see water, you see rocks, some trees, some sky, and you could feel the air around you. And there are, immediately, without even putting a label to it, you can already tell that, okay, there is hard stuff, there is liquid stuff, and there is invisible stuff, right? That's kind of a underlying thing where, obviously, I'm alive, I can see things, and so I can put things into different categories. But how do you begin to describe stuff? Well, first of all, you can say that everything is made of one thing, right? You can kind of think about it as the this is such a bad analogy, but I was going to say it's like a continuous function where even like you can zoom all the way in as far as you want and there's no discreteness to it, right? My hand is made of just more hand when you look closer into it, and the same goes for everything else. Everything is just made of whatever it is made of. But then
Well, I
Yeah,
was
go
just
ahead.
gonna say, well, that happened for like a couple of tens of thousands of years, right? I guess until I guess we were just thinking of matter as continuous. I don't think there are any records of that, are there? Like any writings or any thoughts of, hey, or like what is matter or what is surrounding us? I don't think that was really ever written down. Or I mean, even if it was, not like we have them from then. We have maybe 1 in 5 million that we can recover now. But for the ones that are there, or for the ones that thought of it,
actually, surprisingly, this is just kind of like a little aside, but intuitively, you kind of think that in the past, there were a lot of people. But actually, quick fact, there was a time in human history where there were 50,000 humans on Earth, right? And it's actually after like some catastrophic event happened and it wiped out a lot of humans. But at some point, there were 50,000 humans on all of planet Earth. So, right. That might be why, like, it's just because you said, oh, we only recover 1 out of 5 million records. But it's like,
yeah, maybe.
maybe
Okay,
there
that's
weren't that many
exaggerated,
records
but
to even
maybe there
to
weren't
even
that many
preserve,
records.
right?
Right. But I guess that happened for a long time. Let's just say that happened for quite a long time, until we come into 9th to 10th century BC, right? In this time, it's still pretty preliminary, right? I mean, nobody really knows what's going on, but we're still more civilized than we were, 50,000 years ago. There are still civilizations, I should say. And the first known or at least spoken about, encounter of thinking about particle physics or anything really remotely related to what we're seeing was in India, actually. It was in the Jain culture. And they thought that they kind of split up the world into 2 different parts. And this is kind of intuitive if you think about it. They split it up into living and non-living. I think that's pretty intuitive. And then the non-living part of this universe had a subsection. Now that's where we start to understand, okay, what is this actually made of? And they originally actually thought that, now obviously I'm just going to analogize it, or I'm going to say it as matter, but obviously that was not the word for it back then. But they did understand or think about these rocks or these houses and these huts and whatever as having something in them. Now, they didn't know what that was, but they knew that this piece of equipment has some, not definite, but actually countless number of invisible particles that we can't see or understand, obviously at this time, right? So they thought matter existed, or at least a very simple form of matter. And then over on top of that, they thought that, hey, this matter or whatever, that what is actually making this up? For example, why is a wooden bark different from a rock, right? There's some difference in matter. Just, you can straight look at a piece of wood and a rock and you can be like, that's different. So that's obviously the matter. But when they asked themselves, what does that even consist of? They actually said countless number of invisible particles. Let me see what they were called. They were called permanu. Sure. And they believed that each one of these permanu, each one of these particles contained discrete smells, tastes, discrete basic senses that we could differentiate them by, right? And all of these particles, or these permanu, or whatever you may call it, make up this matter that then we can feel and touch and be like, okay, these are 2 different things. So that was, I believe, like the very, very first, or at least recorded, understanding of our universe. And being like, okay, I guess I can say that it's filled up into something that's smaller that we can't see. Because I think if you really think about like because you have to understand at this time in the human history, everything is philosophy. There's no real science. Like everything, if you think about it, is basically a form of philosophy. None of this was experimentally done, right? It was just thought of. It was just like, hey, like for example, my phone is resting on a textbook. So I'm like, hey, this textbook must have something that makes up this textbook that makes it feel different than this mic, right? So that was not really a scientific method, no experimentation was done, but it was more simply just a thought that was had. And that was mainly the birth of a lot of these ideas, right? I mean, as you were saying, we mainly begun a lot of episodes with philosophy. And I think that's beautiful because that's literally how a lot of this began in the first place, right? So getting it back there, trying to understand this is how they originally thought of it to where we are now. Imagine where we can be in another 2,000 years. Like this was just 3,000 years ago. It's absolutely insane. So.
Yeah. Well, if we get a little bit closer to today, into the era of the Greeks, there was a very famous guy who goes by the name of Democritus or Democritus. I don't know how you say it.
Democritus.
Democritus?
I'm pretty sure that's it. Because
yeah, Democritus. Anyways.
Oh, sorry. My bad then.
He's
like that.
He's a famous guy in particle. I guess not really particle physics, but he came up with the idea. Or I guess, well, there are different schools of thoughts throughout the years, but his idea was that matter is made of these very small, incompressible, indestructible, just little like balls, essentially. They're all uniform and hard and, just balls, which actually, if you think about it, is not that far off. Like it's pretty far off.
I mean, it's not hard at all. It's not solid. It's completely hollow.
But
it's kind of far off, but it's an understanding.
No, listen. If you think about it, this guy had rocks and sticks.
Yeah. No. Okay. For sure,
right.
Of course.
Like to come up with that
up, context. Yeah.
To come up with that idea and have it be like not that far off is pretty darn good. Not gonna lie. So he obviously at the time everybody was a philosopher. And that was his philosophy essentially, on what's it called, on the nature of things. So he said things are made of, like the entire universe is just made of these little balls, and obviously there are different kinds of them. Like some of them have bigger sizes and combinations of if you make like I guess combinations of these make up different looking things. And obviously we can tell how ideas about matter have evolved from there, but at the time this was actually a controversial idea, saying that the entire universe was made of little balls and nothing else, right? Just nothing in between, because this would imply that everything, including the gods, were made of the same thing that everything else is made of.
Well, I don't know if that was a direct implication. Did they think that? Why would they think that the gods are made of the same stuff that they are?
Everything in the universe,
but they're not everything.
Is made
they
of...
made the universe. I don't know what they thought that time. I don't really know what they thought that time. But I'm assuming if they thought like God or whatever benevolent being created this universe, I would not assume they thought that it was made with the same stuff that we are. I don't know.
I'm just saying.
Yeah, okay.
I was doing a little bit of research on the history, and I saw that it was a controversial idea because of religious beliefs. Or is it religious? Is Greek mythology like a religious belief? I don't think so.
Cultural,
actually.
Maybe.
Cultural belief?
Maybe. I don't know.
Probably.
Yeah.
That's just
a little bit of Greek. I don't think much. I mean, not that much didn't really happen. But when was the whole Greek era?
That was like 2000. Am I going too far? I was gonna say 2000 years from today, like back in the past.
Okay.
So around the year
so
zero.
Like
and
like 8
before that, though, like 500 BC, and then like onwards.
Mm-hmm. So going from there to where we are today. Okay, too fast. Let's slow it down. Going from there to somewhere today, let's think about what actually happened. I don't actually think there were many experiments. Like, because there's only so much that our mind can do, I feel, and or mind can see, for that matter. So I don't believe that there was really much advancement in the idea of what the particles actually are till like a good deal later, right? Like 18th, 19th century. Or I guess like 17th, like Newton as well. I guess Newton had some theory of light. I mean, he was completely wrong, or not completely wrong, but partially wrong. But I guess there were thoughts, but the experiments or the actual concrete proof of what's actually happening within this matter that we call, well, matter, right? That didn't happen for quite a while. I believe there was also a controversial like debate going on. I forget when this was, but it was probably like a little bit later, where it was if atoms are infinite or finitely divisible. And the argument that was made was if we take a carrot, I don't know why, but it was a carrot, and if we cut it into enough pieces, cut the half, cut the half, cut the half, cut the half, you know the drill, we'll get to a point where we can no longer cut it in half, but it is still a carrot. So the idea was there are only discrete number of these carrot pieces that still mean that are still a carrot that make up this carrot. Now, if you really think about that for a second, that's actually exactly what's going on. So, because if you really think about atoms, or sorry, if you really think about molecules, because when we say matter, we don't really say atoms. We're mainly talking about molecules. Or sorry, I mean, I guess we're talking about molecules, but they're bunches of atoms. We all know this. But when we're really talking about these atoms that make up, these elements, what actually, differentiates them? Because for a long time now, I don't know how many people will think this is a little stupid. Maybe they're like, oh, you thought this? But like when you really talk about a gold atom versus, top of my head, uranium atom, I used to think that there is like something different about the structure or like about those atoms or about the things that make up the atoms themselves. I'm like, oh, there has to be some kind of fundamental difference between this gold and this uranium, for example. But
technically, you're right.
There is, but the only thing that's different, and I don't know how stupid this is going to sound, but the only thing that is different is the number of these things that make up the particle, that make up the atom. And that is protons, neutrons, and electrons. There's just more of the same thing.
But that is a fundamental difference, though.
I guess it's pretty fundamental that they're more of the same thing, but what I'm trying to say is they're not different things, is what I used to think.
Yeah.
They're not actually different things that make up these two particles that then differentiates them. It's just the same thing, just more of it or less of it. And if you think about it, this carrot analogy is almost exactly that, right? They're all just made up of proton. Now, obviously, the carrot is just one type. It's one carrot. But I'm saying if you think about it the same way in proton, neutrons, and electrons, it's just this one type, or I guess in this case, these three types that make up everything that we see today. And when you differentiate two things, you're not saying, like when you're not, now we get into the more, I guess not philosophical, but more understanding of it. When you're trying to differentiate two things, you're mainly looking at simply the number of these subatomic particles that then make up this atom, right? Now, that's, again, an analogy to, like, what we have today. This was obviously not thought about that back then. This was simply a big debate because many people thought it was, as you were very well saying, continuous, right? Matter could be very well continuous. We didn't really understand how it could be broken up into discrete elements. And then we come to the 19th century. Do we want to start the 19th century? Or is there anything in between that you want to add?
Actually, something that we forgot to mention, just really quickly, is that even before the whole atom debacle, a huge idea was that there were 4 elements, just water, earth, and fire, and air.
Airbend. And
also combinations, right?
Right.
Like if you mix fire and earth, you get metal or whatever. Could you find?
You can make metal. You can make metal.
No, I know you can make
videos.
metal.
I think you're
I'm
the one who showed
saying
it to me.
I'm saying, yeah, I did show you
Yeah.
that. But I'm saying, can you like, did they have the tools to find metal though? I don't think so. But the point is that when, why make it complicated when you can make it simple? And in this description, where there are only 4 elements and everything else is just combinations of these 4 elements, it is kind of intuitive, because you take 4 things that hardly share any properties at all, or no properties, barring the knowledge that we have right now. Right? You have one thing that flows and is a liquid, one thing that is invisible and is a gas, hard earth stuff, and then fire. Like what?
Hard stuff.
Like fire, if you think about it, it makes sense to think that fire is an element, because back in the day, it is as unexplainable as things that are elements today, right? Like, how would you know that fire is not a thing? It just behaves differently. But, it gets placed as an element. And technically today, is fire... What is fire
Don't ask that
plasma?
question. No, what? No.
No, I don't know.
Fire is just combustion, right? So I mean, not technically not combustion.
Right, but like, what is the light though?
So
like-
it is the burning of the wood. So the wood that burns releases carbon dioxide, and shoot, I should be knowing this because I know a lot about fire. I actually love talking about fire at campsites, and now I'm forgetting it because I'm on the spot. I actually know a lot about fire. 1 second. I actually know a lot about this. It's because it's mainly... God damn it. I can't seem to find the
Wow.
words to really put it
Wow.
together right now, and it's pretty embarrassing. I'm having a pretty
You
embarrassing moment.
really let me down.
Yeah, no. I know what
No.
fire is though, mate. Like
It's
because
okay.
It's basically like I can't.
It's fine. All I wanted to say was that you go from putting things into categories, and hopefully, the more you refine your partitions, the more you know about matter itself. We started off with, let's say at this point, we had 4 partitions. But then slowly we started realizing that, there are like also subdivisions. Like if you think about it, if you think about a square, I want to make an analogy to arrays in computer science.
No.
But I won't because this will get way too confusing. But essentially you have this block that you separate into 4, right? Earth, water, air, fire, and all that stuff. But this is slicing it one way. But then you realize that everything is made of different types of particles. And so now you're slicing it a different way, because within the category of earth, you'll have like rocks and you'll have dirt, or I can't even think of other things like gold, silver, copper, right? You start doing like subpartitions of one category. Next thing you know, you have the periodic table. Fast forward in time, right? So I guess that is kind of the general outline of particle physics, I guess. Yeah.
Okay. I want to just forget that whole moment that happened. Okay, please.
Okay, no.
And we start from...
You
and-
looked
and-
up the fire.
No,
You
of course I
looked
did.
it
No,
up.
of course I did. Just to make sure. No, of course I did.
Yeah,
But-
yeah.
My original mistake was doubting the combustion part. Because the moment I said combustion, I'm like, no, wait. And then I started doubting it, and then I'm like, wait, then how does it work? Because combustion is basically just any kind of... Well, combustion is just any kind of oxygenated exothermic reaction, right? I guess any kind of thing that releases energy is essentially combustion.
Which
So
is actually
what
crazy
happens-
if you think about it. Like
Yeah, it's
the
it's
odds
I mean,
that
exothermic-
it would
it's
use
pretty cool.
oxygen as a is it
So-
a catalyst? I don't know the
Yeah,
chemistry
I mean it's
words,
not.
but-
Well, I mean it is. Okay, see that's another one. I shouldn't say the word catalyst, but it definitely. I think it is a catalyst because if you add oxygen to a fire, you know that saying, right? So I guess you can think of
Wait,
it as a catalyst because
I don't think you can call it-
reaction.
I don't think you can call it a catalyst though, because it's required for the
I mean-
reaction, right? So if you take it out of the equation, like it just won't happen at all. But a catalyst makes it go faster, though. I believe.
So this would
This
speed
is
up
why
or slow it
I
down,
didn't do
right?
chemistry, though.
Yeah. So I mean, it would speed it up or slow it down, right? So I would think that because it itself does not exhibit the reaction, it might be a catalyst. Anyways, getting away from topic, fire, just like the light thing. Because when you said that, I'm like, it's just heating up, right? So it's just heat, and like when there's heat applied to atoms, the electrons are like, oh, I'm excited, so they jump, and then when they get released in the air, they're like shit.
Yeah. Okay.
And then they release the photon. So yeah, so I just
Wow.
okay, embarrassing moment there. Let's just again
Very nice
sweep that through.
description.
Let's just sweep that whole thing through,
Let's just
and
keep
let's continue
going.
into particle physics. So
Okay.
let's get into
The
first-
rise?
Oh, you're talking. Okay.
I wanted to talk about this really
Go for
quickly.
it.
The rise of experimental physics. Back in the day, like back in the day when philosophy was the big craze, people wouldn't actually do experiments because they didn't really know what to do, right? Like how do you do experiments on particles with just your hands? There's not much you can do. But now coming into the Renaissance era, I believe, where experimental physics actually became a more important thing. And then you have the rise of statistical mechanics, right? Because you start studying matter, as in like hard stuff, and then you also start studying fluids. And then you start discovering things like the ideal gas law, which actually reflects a lot about the particles that make up that gas. Even though you're making a macroscopic comment on the collection of particles, that actually tells you a lot about the individual particles that are in the gas itself.
Trying to understand, or technically it's also be like stoichiometry almost, because it's like kind of determining like the amount of each molecule that then contends into the reaction, right, that we see. So I guess you can think about it that way too. But I guess now, as long as you don't have anything else to add, we can get into the first experiment that started to understand what are these atoms made of. This was the J.J. Thomson experiment. Famous dude. He created basically a modern day not modern. It's not modern at all, but it's a cathode ray tube. For those of you that need some recollection on CRTs, it's a joke because they're very, very old. So, they're basically just a glass tube, very, very low pressure glass tube. So like it's near vacuum, low pressure glass tube with some kind of metal alloy, right, installed inside. Now this metal alloy, I believe, usually is cesium, and when it's heated, it releases electrons. Or again, at this time, we had no idea that it releases anything, but he just created this glass tube, put this metal piece in, and was like, let's see what happens. What he saw after another part of this cathode ray tube, obviously, how do we actually conduct this electricity, is like two, I guess today what we would call the cathode and anode. I mean, basically you can think about it that way, but it's when you run a high voltage through them, it would create, or it would send heat into the tube, which would then heat up the eventual alloy, which then, let's see what happens, is the idea right now. So they ran a high voltage through it to heat it up nice and good. Cesium alloy, spit some stuff out, and because I believe they also put a gas that obviously would allow things to be visible, which is how they knew that, hey, something was there. And what they observed was that there was a
hold on.
deflection. What?
1 second.
Go for
it's
it.
just because you said it spits something out, and also gas that allows something to be visible. I just wanted to clarify.
Okay, you want to clarify?
No,
Okay.
no. I just wanted to clarify. By spit something out, you mean electrons, right? When you
Well, no,
heat
I
it
mean
up.
the idea is that we see it, right? How do we see it? It's when the electron will eventually collide with the gas and then excite
but
it and
that's
then
what I
release
mean.
light. Right.
When you
exactly.
heat it up, it spits out electrons, and then the electrons interact with the atoms in the gas, specifically chosen so that it releases like a photon of a specific wavelength through that interaction, and then you could see that there is something happening.
Exactly. So
Is
what
that
we
is
saw,
that what happens?
yeah. So I mean, there's
yeah.
because I mean, I'm assuming it's similar to the charge experiment, like the what was that? What was that called? The one that I did. I literally did this last year. It's similar to the charge experiment, where
the mass ratio.
yes, exactly, the mass ratio. I mean, the mass ratio was like our thing, but the charge was just like the fundamental charge. And so like that whole experiment was done by putting, I believe it was helium, in the tube, which would then again, when you excite it, it creates like a blue light, and then we would eventually see that. So what they again saw were these light rays, or these rays again, deflected towards the cathode. Right. And then they, well, basically from that whole analysis, they discovered that, hey, this alloy is releasing these things that for some reason is going towards the positively charged plate of this electric setup. What must this be? Hence the discovery of the electron. So that was the first thing that was discovered in all of the atoms, because I guess it's the easiest because it's very far from the nucleus as well. Also, electrons, as everyone knows, like to leave the atom via electricity, right? So that was also a very big moment, right, for the whole community in science, because I believe there were a lot of other individuals as well that contributed to similar experiments that also similarly found, different like basic things again at this time that were moving towards these positively charged plates. And the only understanding from that was that this metal alloy is releasing something that is moving towards these positively charged plates. Hence, this something, number one, has to be from this metal alloy. Number two, has to be able to leave the metal alloy easily. And number three, moves towards a positively charged plate. So, I mean, now we can infer all those properties as properties of a metal, and therefore consisting of electrons that are free to travel. So that was a pretty big experiment that kind of got us into electrons.
And in parallel to studying fermions, right, which we will talk about what a fermion is, but as you now know, an electron is a fermion. So in parallel to studying fermions, people were also studying radiation and light. As far back as, even way, way before Newton, but Newton came up with the idea that light is a particle. And it should fit, obviously in this categorization of all that is, in this world, would be, alongside all of the other particles that we know of. And although that is, like a somewhat half false statement, it is a very bold statement to go out and say, even having it been confirmed by Einstein later, it gets very confusing. But, if you want to know more about like this specific topic, we do have an episode about light. I think it's called What is Light?
No.
Something like that.
We call it something funny, I believe. The light one. No, I remember that. I don't know what it was called though. Yeah.
We talk about this whole thing, but essentially it comes all the way, across this study that you just talked about, discovering the electron. In the background, there are people like Max Planck discovering that energy is quantized and that photons are emitted in, single packets, but can be described by a wavelength. And so as we're discovering particles like the electron and then later the proton, people in the background are discussing ideas about quantum mechanics. And as we keep talking about different experiments, you guys will see how this kind of like quantum mechanical, I guess like you can call it like a just a background, just completely takes over. Because at the end of the day, as I've said before, actually, I forget, somebody sent us an email who quoted the podcast in one of their papers, one of their like high school papers. And one of the quotes was that I said that the world is, we can kind of forget about classical mechanics because the world is inherently a quantum world. And actually, I just wanted to clarify really quickly that I'm not saying that quantum mechanics or classical mechanics is useless. It's very useful, especially because we are classical objects and we study classical things all the time, like planets and stuff. But you can always reduce everything to a quantum mechanical problem. And now segueing back into particle physics, that is why things got so blurry at some point, because all of a sudden what we thought were particles, like electrons, are suddenly being described as waves. So this kind of shift in ideas was happening in the 1900s, where people were kind of asking themselves, do we even know anything about particles at all? Because our entire worldview is being turned upside down right now. And to be honest, instead of answering that question, in the present day, we've just learned to accept it, right? We've just learned to accept the weirdness of what happens at the fundamental level. Yeah, that's just what I had to say.
So that's a pretty big part, right? The whole quantum mechanics, classical, I mean, I guess not classical, but discrete versus wave-like debacle was a little bit interesting, because we think about these particles very differently now, I guess, because of the introduction of these kind of individuals. Now, I believe Planck was when? Planck was like 1920s? 10? Like, when was Planck?
Well, he came out and said that energy is discrete in,
right.
I'm very positive that it was in 1898. So Einstein was just a little kid at the time, not really a physicist, or actually,
not a kid. He wasn't a kid.
That's not
1905
true. He was a
his biggest
teenager.
year.
He was a teenager.
Yeah.
But yeah, it was announced, I think. I was gonna say before Einstein could even use those ideas in his studies, which, I love thinking about the timeline of events that happen in physics. So that's why I brought up Einstein. But I did want to come to a couple of experiments that definitely shifted the ideas in particle physics. One being the photoelectric effect, and the other being, is there a name for this? The gold foil experiment? Is that what it's called?
Rutherford's gold foil experiment, yeah.
Rutherford's gold foil experiment. So you can kind of tell, I don't think they really had a choice, but you can tell how people were designing experiments based off of their classical understanding of the world, right? If you think that particles are like little bowling balls that just fly around and hit each other and bounce off of each other, then what else would you do but design an experiment where you send these bowling balls to a wall and you see how they bounce off of that wall? That was Rutherford's gold foil experiment. He sent alpha particles to a little thin foil of gold, and alpha particles are positively charged, which means that if it encounters something else that is positively charged, it will be repulsed very hardly. Is that a word?
It will be
very strongly.
Strongly, there it is.
very strongly. And actually, that is because of the electromagnetic force, which is much longer range than the strong nuclear force, which is why you might be thinking like, oh, how do protons actually stick to each other in the nucleus, but then actually when they're far from each other, they repulse each other. I've dug myself a big hole because there's so many things to talk about right now, but I'm going to go back to the experiment. What they notice is that, okay, a lot of them go through. a lot of the alpha particles just go straight through the foil, which means that there are no interactions happening. But sometimes they get deflected and they go off, and sometimes they even get deflected and go back towards where they were sent. And very rarely, though, which means that a very good explanation for this, which happens to be true, is that there are these very small packets of positively charged things inside of the gold foil that are very spaced out from each other. And, it leaves a lot of room for the alpha particles to just go right through. But when they do encounter or get close, they kind of roll up the electric potential hill, right? And get deflected at a certain angle, or even go up and then turn right back around because of the interactions. And so there is when we learnt actually about the proton, the positively charged particle.
Well, first we technically learned about the fact that, there's a nucleus in the first place, because at this point we only understood that there's an electron.
Yeah, right.
So first we understood that, okay, if it was only electrons, or again, whatever this really composed of, it should be always, attracting to this particle and not deflecting in the way that it did. So that meant that there was something else in this gold that we didn't know about, and that was hence named the nucleus. So I believe that was the first thing.
Actually,
and then it was
ideas about atomic structure were already in place by the time that Rutherford made his experiments, which was in 1919. So ideas about the structure of the atom were already quote unquote known, but this experiment was evidence of the existence of the proton. Right, so people already had the idea, right? Like there's the old idea about the plum pudding with the positively charged cloud with the electrons inside of it. And then they had ideas about the nucleus existing with the electrons around it. This was actually just proof that protons exist, and the nucleus, is a thing.
Yeah, Rutherford did some pretty cool stuff otherwise as well in particle physics. One of the big things he did was nuclear fusion. It's kind of funny that he split the atom, but he didn't discover nuclear fission. Someone else did and took the Nobel Prize for it. It's kind of funny. But so he discovered nuclear fusion, which is still pretty cool, right? Where, I believe he took deuterium, which is like an isotope of hydrogen, and he mixed it up with some nitrogen under an adequate energy. And he found that it creates these hydrogen ions, or technically just protons, and a lot of energy. Bada bing, bada boom. Rutherford discovers nuclear fusion. Add these two things together and you get nuclear fusion. So at this time, though, a lot of questions can also be asked, as in like, how did we know a lot of these particles even existed? Because like when I was doing my own research, I was asking myself those questions. I was like, well, how did we know? Because, for example, we already theorized that nitrogen, for example, was composed of a lot of hydrogen. But then when I was going onto the dive onto like how did we discover like that like what these hydrogen nuclei are, and how, because hydrogen nuclei were named protons after the discovery of protons and understanding what they are. So my question was, well, then what do we really call hydrogen nuclei? Or like how did we really understand them? And I think at that time, it was just thought of as like a fundamental unit. If I'm incorrect, please someone correct me and send it to us, because I am actually curious about that. It's something that I couldn't really readily find online. So the hydrogen nucleus was understood, semi-understood at that time. And when it was found that a lot of these nitrogen atoms basically inhibited properties of a nitrogen atom inhibited properties of a lot of hydrogen atoms, they could make the conclusion that hydrogen atoms exist in everything. And therefore it was called, well, the proton. So the singular proton, right? So, or at least the ion, the hydrogen ion, I should keep saying. So that was the original understanding of at least a little bit of hydrogen, which is when they got into then later something like deuterium, because they understood that water, or I don't actually, did they know the chemical composition of water back then? Probably not.
I would say probably, actually,
because when
because the periodic table was
Right,
periodic
right.
table
That's
was
that's
being-
true. That is true. That is true. So yeah, you might be right actually. Sorry for, again, one more slip up. But when you distill it in a certain way, with certain chemicals and whatnot, you can basically split the H2 from the O. It's a nice way to say it, but that's not what actually happens. But that's basically what happens. So H2, you get an isotope of deuterium, an isotope of hydrogen, which is basically an extra nucleus, right? And that combined with this nitrogen was found to produce this a lot of energy. And therefore we could then conclude, or not conclude, but therefore we can say that this form of particle interaction creates a lot of energy. This very highly exothermic reaction that then we went on to call nuclear fusion. So that was a pretty cool feat as well on Rutherford's part, right? That was the electron, neutron, and proton discovered. I believe the next one was the positron, right? Was that an actual discovery or was that a thought?
I don't know.
Because at this point,
I just
right,
don't.
I would think we understand what electrons are to a certain extent, right? We understand they have a charge, some unit of charge. The way we can compare charges is by comparing the amount of electrons, right? So we can just divide it by, let's say this hydrogen atom has 1 electron, divided by that charge, or technically it's neutral, but the idea is there. So understanding, again, there are a lot of charge experiments and whatnot. We've spoken about I keep wanting to say Milken, but I don't think is it the Milken charge experiment? That's probably what it's called.
That is the oil.
That's the oil one, right. So it's not Milken then. It's a chart. I don't believe I'm forgetting this guy's name when I literally did his experiment. This is very embarrassing again. I'm not having a good day at all. But anyways, so we understood the charge and whatnot of these electrons. We also understood the mass because the charge to mass ratio, or in terms of electron volts, was very well understood. So in the positron, I could only think, I couldn't be particle accelerators because that was way later. Because a positron is basically an electron, as in the same mass, same magnitude of charge, simply opposite sign. So it's basically an electron, but it will deflect towards the negative side instead of the positive side. So that's actually probably how they did it, to be honest. But where did they get a positron from?
I didn't know. For some reason, I thought the positron was an unstable particle. I don't know if that's
unstable
right.
As in, like it decays into something else?
Yeah, not decays, but I think it annihilates fairly quickly, right? The lifetime of it is not very long.
Yeah,
unless I'm thinking of a different particle.
No, you are correct. They actually do. Positron emission is a subtype of radioactive decay. Oh yeah, positrons get. Oh, that's probably how. Because yes, in a very similar manner, they probably, because it's called beta decay. So it's just shooting these different types of particles towards the same material. And I'm assuming that's, okay, there it is. So they probably shot, again, this is just a guess, by the way, so don't quote us on this, but they probably just shot these particles, or these understood, beta particles, which are, again, basically just combinations of protons and neutrons, a select number of them, into these materials that were understood to have these particles, and then it therefore created, or it also released today what's known as a positron. And I'm sure what was done, because how else would they have done this, had some kind of electric feat, right? Like some kind of positive negative side, basically, so that one deflected towards the positive. I'm sure that's most probably
towards
how
the
they
negative.
discovered it. Towards the negative. So I'm quite sure that's because most experiments, when it comes to charge determination, because again, it's the same thing as an electron, so it's kind of hard to determine it just by itself. But when you're trying to determine charge, you're trying to see, well, how much is it deflecting, right? So the deflection actually is pretty important in a lot of experiments that then actually happen to go on with electrons, with protons, and with understanding them even further, right? Wow, we are almost an hour into the podcast, and we've not spoken about fermions, leptons, bosons, the whole standard model.
Yeah.
Oh goddamn.
Well, a nice segue into those ideas is that, okay, now we've spoken about kind of these. I don't want to say the word because it'll spoil it, but I guess I'll just say these particles as a placeholder. We have like these neutrons, we have protons, electrons. Now, if we fast forward a little bit down the line to kind of in the 60s, 70s, 80s type deal, people start, asking even deeper questions. Maybe protons aren't the end of it. Maybe we can even go deeper. Where scientists in the community started putting forth the idea of quarks. Quarks are actually even smaller particles that actually make up, is it baryons and mesons?
Well, quarks basically
right?
make up most of everything that we can see and feel and touch. So
Sorry, not baryons. The thing is, I've
hadrons
always
is
had a hard
technically the term.
time.
Hadrons is the term. So
Hadrons, yeah.
hadrons are the. So when we say like Large Hadron Collider, because I know probably every single one of you listening knows what that is. Hadrons. I mean, there are a lot of terms in. Okay, sorry. The
I wouldn't
LHC in
assume.
Geneva. Sorry, it's a very large particle accelerator in Geneva. It's called CERN. Probably heard about it. And the Large Hadron Collider is one of the most famous particle accelerators to exist. And it's called a Hadron Collider, like most other particle accelerators, because hadrons are one of the most common, or the most common type of particle pair there is. So quarks can't really exist by themselves. Quick fact. It's like a single quark can't really exist because the only thing that it can do is interact with the strong nuclear force and bind to other quarks. So two or more quarks in a particle basically creates what we can call a hadron. So common things like protons and neutrons are three separate quarks. It's, again, getting into what they actually are. I guess we can go into it a little bit later, but
Those are baryons, first of all.
what? Yeah, baryons are
Particles
three.
that are made of
Exactly.
three.
So baryons
Mesons
are
are two, right?
Baryons are technically mesons are a quark-antiquark pair. That's different. That's even more different. But so baryons are a subtype of hadrons. Now these are going to get very interesting terms very soon. So baryons are a subtype of hadrons where there are only three quarks present in this particle. So baryons are what we can call like baryonic matter, for example, is a very common term that we probably use in a lot of astronomy episodes, because in the initial stages of the universe, that's basically what was there, right? Protons and neutrons is again baryonic matter. That basically again makes up the fundamental. Sorry?
How initial are you
Okay,
talking
well, yeah,
about?
not like initial. There's actually a theory. A quick aside here, because I said quarks can't exist on their own. There's actually a theory, and this is most likely what happened when the energy is very, very high, and it's just very, very high on everything, basically. There's the other state of matter called quark-gluon plasma, where the quarks and the gluons literally separate from each other, and they're kind of existing all in a pool of this plasma, which we call quark-gluon plasma. And it's theorized that that's originally how a lot of this started. This very, very hot, dense environment, which was a quark-gluon plasma, which then cooled down, which then forced all these quarks to then bind together with these gluons. So, yeah, so those are basically hadrons. Those are basically baryons. The word that Parker just mentioned, mesons, are something even crazier, which is a quark-antiquark pair. What is that for a lot of people? So antimatter is pretty interesting. So we've been talking this whole time about the theory of matter. If you can search up really quickly like how antimatter was exactly discovered, that would be really cool. Because I don't know if it was discovered or theorized. Because if it was theorized, that would make sense to me. But how it was discovered, again, maybe they just thought of it as, again, the similar thing to the positron, because the positron is antimatter. So it could be simply thought of as, okay, is it deflecting in another way? Like, does it share similar properties, but it deflects somewhere else? Maybe they thought of it that way. But again...
Okay, well, antimatter actually was the idea began in 1928 by Paul Dirac. He was studying the relativistic version of the Schrödinger equation.
Wow.
And essentially it predicted the possibility of anti-electrons.
So it was math first. So it was the thought. That's fantastic.
Yeah,
So
yeah,
so
it
when
was,
math
yeah.
started, again, then positrons were discovered, and that was the first discovery of antimatter, right? That was the first discovery of, hey, matter can have an anti-side of it. And then we start to basically understand that all of matter has an anti-side of it. Now, they're not stable, as we very well discussed. Stable because they decay into subsequent matter. The whole antimatter thing is kind of a whole breeze. I think we've spoken about the whole baryon asymmetry problem. That's a whole fantastic episode. But yeah, so antimatter is a whole subtype, and mesons are a pair of quark-antiquark pair. So it's a subtype of hadrons, which is the whole big thing. And yeah, those are mesons. And the reason now you might be thinking, how don't they annihilate, is because the strong nuclear force is actually preventing that. It's so very strong that it, I guess, doesn't allow it to annihilate. Now, again, these are very unstable particles again. So it does actually eventually annihilate. But for that quick second that it is actually there, such as in particle accelerators, we can understand their properties. So hadrons are this whole subsection, right? Where we can understand, where we can bombard these particles at very high speeds and we can see what happens. But then there's another part of the whole world. Or actually, there's two more parts of the whole world called leptons. And then bosons are another part. Leptons are another fundamental part of the universe. And that is what we call our friendly electron. So our friendly electron, interestingly enough, is not composed of subatomic particles, right? It is its own fundamental particle. How that was theorized, or, I mean, it is very, very much lighter than the proton and the neutron, right? So there's probably that. Wait, man,
Isn't...
it's like 10 to the 3 difference.
Oh,
right?
no. No. I was thinking about proton to neutron.
Yeah, proton, neutron.
Neutron's a little bit heavier.
It's basically, yeah, but you can, usually in calculations, we take them as the same because Astro. But yeah.
Actually, that's not true, though.
Oh, I remember that one problem where no, I remember what you're talking about. I remember that one. That's exactly what I thought of. So yeah, so leptons are another subsection. So let's just go over that really quickly again. So quarks, there are like six flavors of quarks. They're called flavors because it's delicious. And what they are, again, not that this matters. I'm just gonna name drop them, but it's probably not gonna matter. Up, down, top, bottom, strange, charm. Strange and Charm were very interesting names to me, especially because I believe one of them was called Strange simply because of its spin? No. Why was it called Strange? It was called Strange because of something. Again, they're all named for some reason. But again, the names are kind of arbitrary. It's just different types of them.
Arbitrary.
Yeah. But up and down basically make up everything that we know. That's basically what you need to know. Up and down quarks make up all of the universe. Protons and neutrons are made up of those, just different combinations of them. And then leptons are a whole new category, right? So they're electrons. That is one type of lepton. Another one that's very famous is called the muon. That is actually found in cosmic rays. So when cosmic rays were detected, hits our detectors, it released this particle that was like the electron, but heavier. Now, as in like the electron, I can't definitively define that. But I believe the properties, again, that they understood from it were similar, as in it is indestructible, as in it's not made up of anything more fundamental, right? No understanding of the strong nuclear force. One big
Disclaimer,
thing,
though.
one big thing that I want to mention that I did not mention. And this is the most fundamental difference. Because, again, I've just been saying all these names, and I don't know how entertaining it is to listen to me saying all these names to you. But biggest thing, the difference between quarks and leptons, and here's the fundamental, like when I say how do they know that the muon is not a type of quark, right? Because quarks interact with a strong nuclear force. Leptons don't. Leptons only interact with the electromagnetic and the weak nuclear forces. So again, if you haven't heard about those, we're going to maybe come into it in a second. But that's part of the third category. We'll get into that. But that's the major difference between these two subtypes of particles. And these two subtypes of particles, I'm gonna spit another name for you. fermions. Another name. Boom. Fermions. Now again, hadrons are collections of these fermions. So hadrons, mesons, baryons, all those names that I gave you are just combinations, right? But when we're talking about the very fundamental has two things: fermions and bosons. Fermions are quarks are a part of it, leptons are a part of it, and then bosons are something else. What differentiates these two, you might ask? And that is something called quantum mechanical spin. I believe we've spoken about this various episodes. I'm sure Parker can get us back up to speed if you want. But the main difference is that bosons have whole number spins and Yes. Fermions have
right.
integer spins and bosons have whole number spins. So the spin is just
half integer.
half integer and whole. Sorry, that's what I meant. So that's the main difference. The spin, again, maybe if you want to do a quick recollection on what that is, you can do that. But that's the main difference between all these types of particles, and that's basically our standard model today.
I guess refresher on spin. Nobody knows what it is. There you go.
Well, yeah, no, the best way to think about spin is this. Think of a ball and think of it spinning. But it's not a ball and it's not spinning. That's spin.
There you go. Spin is just a property that we call spin because it has something to do with angular momentum. Okay, actually, it's actually kind of cool. So when studying, when quantizing angular momentum, which happens when you try to describe the hydrogen atom using quantum mechanics, you see that there are different states that the electron can take, and these states are discrete, obviously, the whole quantum thing. But it turns out that even in the ground state, there are two different possible orientations, quote unquote. And this is what the spin is, right? You can have upspin or downspin. And this is called intrinsic angular momentum because it's actually a property of the particle and not something external. Like if you were to imagine a planet going around the sun, that the act of orbiting, right, gives a quote unquote external angular momentum to the planet. But actually having the planet rotate about itself is quote unquote intrinsic angular momentum. It's the exact same thing, except it's not the exact same thing because the electron is not actually spinning. It's just something that we can measure, right? So think of it like that. We can measure it, so it's a thing, but we call it spin because we tie it to angular momentum, but it's not actually spinning.
Right.
And I'm not even going to talk about why it's half integer and integer.
Yeah, that's a little too much.
It just gets very complicated.
Why the numbers exist are quite far of the scope of this particular episode. But the only difference is, again, half integer is the fermions and whole integer is your bosons. And that's and maybe that's a nice transition into bosons. Well, what is this third? Again, third as in like quark, lepton, boson, but technically second. It's all the same thing. What are these bosons we speak of? So when Parker mentioned in the very beginning of the episode field theory mainly deals with bosons and mainly deals with things that produce these fields. So what are these particles? So these particles, when we think of excitation in the field, like that term, that's the best way to think about it. Think about the whole universe surrounded by the strong nuclear force, the weak nuclear force, just these names that we've given to these things that we don't really understand. The gravitational force, again, not that it's a force, but that's a name that we've also given it. And then, what am I forgetting? And then the electromagnetic force or field or whatever. So in this case, when we say bosons and when we say excitations in the field, we're basically saying that these fields, again, similar to basic quantum mechanics, have a probability or a wave function. You can call it like that. Have a probability distribution. That means there's a percentage of a chance that this field is excited in this location, and a higher percentage that it is excited in this location. Which is why if I want to punch my hand through the wall, I can't just teleport my hand to the other side, because it's a lot more probabilistic that it remains on this side. So again, that was a very, very basic analogy, but that's like a way to think about these ideas. So the difference between the boson and the fermion, or at least the way that I think about it, is that fermions make up stuff and bosons make that stuff do stuff. It's kind of how I think about it, right?
Because bosons, the kind of way to explain what a boson is it's a force carrying particle.
Yes,
aka interactions, how things talk to each other.
Exactly.
So electrons talk to each other with photons, and quarks and baryons talk to each other with gluons. And hypothetically, not hypothetically,
The graviton.
I guess
It's
hypothetically,
It's very hypothetical.
everything talks to each other with gravitons. And then also there's the weak interaction, which is they have really boring names. W and
The
Z
W
bosons.
and Z bosons. Yeah, W plus,
Yeah.
W minus, and the Z. So again, those are just, again, how did we discover them? We just saw that different, energies, different particles that were being detected, with different properties, mainly different spins, were seen to do different things with this, with similar like reactions, right? It was seen that when, again, I can't really pull this out of my head right now because I don't really know particle physics in and out that much, but I'm sure when we, look at W and Z bosons, we can compare that, or we can look at those interactions with electrons, for example, and we can say, when this boson interacts with this electron at this, like Feynman diagrams, for example, it creates something else. Like, for example, the most famous Feynman diagram, when two electrons are coming together, they exchange a photon and then deflect, right? So that's the electromagnetic particle, technically, that they just exchanged. And that exchange basically pushed them apart, right? Or that's technically what we call the repulsive force. So like when we really think about just like touching things in general, I think I mentioned this somewhere, but like when we're touching things, we're not really touching anything, right? Like nothing is really touching each other. Like it's all just forces that are being felt by us. So like, for example, when I'm touching my screen there, like it's simply the more I press into it, the more repulsion is being created by these electrons with my iPad, for example, and my thumb. So the more repulsion is being created, the more force technically I'm feeling. But again, we just perceive it as touch, right? So all that they're really doing is simply exchanging these bosons. And that's simply what creates the feelings and whatnot and everything that we see. So independently, they can't really do anything, right? They need to all be together to actually work in the universe. An electron needs the photon. Quarks literally don't exist without the gluon. So these things kind of come in unison, and it's kind of beautiful
Not
that we know.
quarks.
What do you mean?
Quarks can exist without gluons. It's
Quarks,
baryons.
they can't be singular quarks.
Well, I mean, if gluons didn't exist, then they would have to go somewhere.
Probably not, because then nothing would really exist, because gluons are the reason why everything exists. Like if you think about it,
at some point though, quarks were not together.
the quark gluon plasma,
Right?
that was the only point
Yeah.
in the
Okay.
universe. But it was still there
Okay,
were still
but-
gluons in there. It was just so hot and dense that they didn't
know.
really bind together.
I know, but if you were to just filter out all the gluons, then the quarks would just be
No, I don't think that's how it would
spazzing
work.
out all over the place.
I don't think that's how it
Like,
works.
where would they go? Where?
No, because
where would they go?
I don't think you can kind of frame the question that way, because you're kind of saying like, oh, what if the Big Bang didn't happen? This would happen, kind of thing. Like you can't really say that.
Sure.
But because you're trying to say like take out the most fundamental thing that created everything. Like you can't really say this would happen if that happened. Because I can't say it won't happen that way either. But I don't think you can say that this will happen. I don't think today, to our knowledge, quarks can't exist by themselves. Unless it's like, again, very hot, very dense in that similar universal beginning environment. But today's understanding of it, That can't really happen. Again, the Standard Model is still very much incomplete because we've spoken about the muon G-2 experiment before, where they very recently last year discovered that the muon spins a little bit more than it should, and just that enough basically means that, hey, our theory of the Standard Model, something's missing. So there can be so many things, there can be another particle, for example, or there can be, a whole new set of particles. For example, well, let's not get into it, but there can be a lot of different types of particles that, constituent matter. It's just that these are the ones that we can understand, we can perceive, sort of, to our current level of understanding. Like, who knows, in 100 years, you think we're going to get 2 more particles?
Yeah,
Probably.
Might be a lot more.
Who knows?
Now, in an effort to not articulate concepts that should be, read or
Right.
studied, not through your ears, we are going to end the episode here. I hope you enjoyed this kind of like overview, history lessons / present day understanding of particle physics. If you did enjoy, make sure to like and share and follow on Spotify. We're almost at 30,000 followers. Isn't that crazy?
That is absolutely crazy. I think we're at 600,000 downloads, are we not?
No,
I could be wrong.
we're not.
580? 550?
No,
Oh,
no, 550.
God. 550? Okay. Close.
Yeah. So go subscribe to us on YouTube. Go like this video. Yeah. Thank you so much for listening.
Also, if you want, please feel free. We love the comments. I mean, that's why we did this particular episode. We've already done particle physics episodes, but I guess we've never really done it in this way. And we got a lot of comments talking about particle physics. Why don't you talk a little about... We got a lot of dark matter comments too, which I don't think we can do quite yet. Maybe a professor would be better. But I think this episode kind of just finished a lot of our current understanding of the Standard Model and of particle physics, because I think anything deeper than this, we would have to get like a licensed professional into the podcast. So, I mean, that's obviously not the end of the particle physics, but I think for us currently, to our current understanding and knowledge, that basically wraps it up.
Yeah. All right. Well,
Yeah.
Thank you so much for listening to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we shall see you soon.
Bye, guys.